Just like charge and energy, the number of quantum computing research programs seem to be a conserved quantity as well. When Google was shutting down its quantum computing program Willow, Microsoft unveiled its all-new quantum processor, Majorana 1. There are many videos and articles about Microsoft's new topological core, but very few resources actually explain the technical terms that are being used. So, while planning this video, I tried to identify one concept that's the most important for understanding Microsoft's approach. In this video, I'll explain the fundamental building block of Microsoft's topological computer as simply as I can. And mind you, they're using some truly exotic particles in their quantum computer. Stick around till the end so you can actually understand what makes it so special. The most important component of a topological computer like Majorana 1 is something called MZMs, or Majorana Zero Modes. To understand that, we first need to understand what Majorana fermions are. But actually, even before that, it's probably a good idea to start with quantum computers themselves. You see, quantum computers don't use normal bits for processing information. They use quantum bits, or simply qubits. However, qubits are extremely sensitive. Imagine encoding information in a qubit made up of an electron. If a wire passes nearby, which is very likely in a computer, it can disturb the electron's state, causing the information in the electron to be lost. So, what's the solution? Simple really. Conceptually, split your electron in two while keeping it whole physically. And these parts will now turn out to be neutral in charge, even though the original electron is actually negatively charged. Now, take a second to think about how counterintuitive that is, but this is exactly the principle that topological quantum computers use. And I know some of you may think, "You're crazy, man!" But give me 5 minutes and I'll explain exactly what I mean. First, let's create a formalism to describe electrons. When a physicist wants to create an electron somewhere, he raises his magic wand, pencil, swishes it around in this shape and chants "C dagger," and thus an electron is created. Okay, but seriously, when we want to express any idea roughly along these lines, we use the notation C dagger. And similarly, we use C to mean the opposite. It destroys a particle that exists. Now, for this reason, C dagger is called the creation operator and C is the annihilation operator. And know that there is much more rigorous theory and elegant mathematics behind these concepts, but for the sake of this video, treat this as just being notation. Think of it this way. How do we describe a particle's existence or creation when solving problems on paper? These operators provide the answer. For example, having an electron in real life corresponds to a C dagger in math. And don't worry about how electrons are physically destroyed or created. This is just a mathematical tool for now. Now, let's decompose these operators into real and imaginary parts. Just as we can write 5 is equal to 2 plus 1 times 3, we can also write C is equal to gamma 1 plus I times gamma 2. Just that here, instead of 1, we have I, which is the square root of -1. And the minus sign in the C dagger, that is to make the math consistent. You see, the dagger symbol in the creation operator is not arbitrary. It shows that the creation and annihilation operators are related by the so-called adjoint. Here, the adjoint operation simply flips the sign of the term with I. So, to find the creation operation that is consistent with this expression of C, we have to take the adjoint on both sides, so that on the left we get the creation operation and the adjoint on the right side just flips the sign of this term. And that is exactly what I had written for C dagger. This kind of a mathematical splitting is what I had in mind when I talked about splitting an electron in two. For now, this is just mathematical, but in a topological quantum computer, there are particles that are far apart from each other that, taken together, not moved together, but one considered together, act as if they are a single electron. And this is really the whole point of a topological quantum computer. Here, we'll try to get a feel for these exotic particles which, taken together, act like an electron. If you're with me so far, I think you find this video quite interesting, so why not leave a like? Just as we had C and C dagger operators for electrons, let's just say that gamma 1 and gamma 2 are also operators, but for a different kind of particle. Our calculations were purely mathematical, so whether such a particle even exists, we don't know yet. But let's just press on and ask, if it exists, what properties does it have? And what do the gamma operators do? Do they annihilate or do they create? And by the way, notice that if such a particle even exists, then in a sense, it is half of an electron. Again, not physically, but conceptually. This is because we obtain these gamma operators by decomposing the operators for the electron. Now, interestingly, when we rearrange the terms to express gamma 1 and gamma 2 in terms of the original creation and annihilation operators, we find something pretty cool. If we find the adjoint of gamma 1 and gamma 2, we find that gamma 1 dagger is equal to gamma 1, and similarly gamma 2 dagger is also equal to gamma 2. This means that the creation operator equals the annihilation operator. And in terms of physical particles, it means that the particle is its own antiparticle. Such a particle is called a Majorana fermion. Being their own antiparticles, Majorana fermions are charge neutral. Let me explain. When particles and their antiparticles collide, they annihilate. Thus, the charge of those two particles also disintegrates. But charge is a conserved quantity, just like energy and quantum computing research, of course. So, antimatter must have the opposite charge of matter. That way, the total charge before and after is zero. But Majorana fermions are their own antiparticles. So the only way charge can be conserved is if the charge is zero, and thus they have to be charge neutral. This property makes them less susceptible to external disturbances, as there is no charge for nearby wires or fields to interact with, thus solving the problem which I introduced in the beginning of the video. Under some special conditions, these Majorana fermions can emerge in topoconductors. Moreover, they have zero energy. Now, such Majorana fermions with zero energy are called Majorana zero modes, or MZMs for short. It turns out such particles can indeed exist, and they are the kind of particles that Microsoft is trying to use in their quantum computers. Not only are they charge neutral, but they also exhibit some very nice properties like topological protection and non-localization, which makes them an excellent candidate for realization of qubits. But how do we actually get these MZMs in the real world? And how do properties like topological protection and non-localization actually help? And where do topoconductors and topological computation come into play? These are all very deep questions which we won't have time to cover in this video. But if you are interested in learning more about the inner workings of Majorana 1 and topological quantum computing in general, make sure to leave a comment or like. If there is enough interest, I'll make a video delving deeper into the more technical aspects of this technology. Note that some researchers are critical of Microsoft's findings. Some problems have already been pointed out, so take the contents of this video as being the theoretical foundation of what Microsoft is trying to do. Let's sum up. We started out by exploring the main problem in quantum computing: making noise-resistant qubits. Topological quantum computation tackles this using MZMs, which are inherently resistant against various noises due to properties like topological protection. Here, we focused on understanding the Majorana zero modes, which are the zero-energy Majorana fermions found in topological superconductors. Majorana fermions are their own antiparticles, which we saw by splitting the electrons' creation and annihilation operators. Though our analysis was mostly theoretical, there is indeed some experimental evidence supporting the existence of MZMs. If you're someone like me who's perpetually fascinated by quantum physics, you definitely want to check out this video on one of the coolest experiments in all of physics. I hope you liked this video and don't forget to like and subscribe. I'll see you in the next one.